this is the solutions for assignment 10. Number 1, how do airbags reduce the risk of injury during car accidents? Use impulse and momentum in your answer. So let's say we have a head-on collision. A car just crashes into like a wall or something, maybe a barrier on a highway. The momentum of the car will very quickly go to 0. It'll go from something to 0 very quickly, which means it's going to have a large impulse J, and this impulse J is equal to Ft. So no matter what, the momentum is going to go from something to 0, and that's going to keep the impulse J constant. So what can we change? We can change the time that the impact takes. So if we increase the time and the impulse J has to be constant, then the force has to decrease. So therefore, airbags reduce risk of injury by increasing the time that the force is delivered over. So by increasing the time of impact, it lowers the force. That is because the impulse is constant there. Number 2, two students are having a disagreement about momentum and kinetic energy. Student A states that it is possible for momentum to be conserved while kinetic energy is not conserved in a collision, while student B disagrees and says that if momentum is conserved, then kinetic energy must also be conserved no matter what. Who is correct? Correct is student A, and we will see why shortly. Explain your answer using the conservation laws of momentum and energy. So let's say we have some mass and another mass, and they're moving together. They both have mass of m, and they're both moving at speed v. So therefore, the initial momentum is equal to 0, and after they collide, they are just stuck together, both with a velocity of 0. Your final momentum then, in this case, is also 0. Now, initially, our kinetic energy total is not 0. They both have kinetic energy of 1/2 mv squared and 1/2 mv squared. So the total kinetic energy is actually just mv squared. But at the end, they are both at rest. So your kinetic energy does equal 0. Therefore, the kinetic energy is not conserved. We go from some amount of kinetic energy to 0. But momentum is conserved in this case. So student A is correct. For question 3, for the following scenarios, determine the type of collision, what quantities are conserved, and what quantities are not conserved. So for A, a metal bat collides with a wooden block on a smooth floor. You hear a loud thud, and the block slides away while the bat stops almost immediately. This here is inelastic. I know this because I'm told there is a loud thud. So some energy lost to, and that would be kinetic energy, sound. What quantities are conserved? Momentum is conserved. And because it's inelastic, EK is not conserved. Part B, head-on collision between two test vehicles where they both come to a complete stop immediately after the collision. This is inelastic. And I know this because kinetic energy is not conserved. We go from, let's assume the vehicles are identical for this quick example. We go from a total kinetic energy of mv squared to 0 because they both come to rest. Momentum is conserved because it is a head-on collision if they are identical. And then it comes to 0. We can assume that they are identical because we are told that they come to a complete stop immediately after the collision. So we can say that the initial momentum is 0 and the final momentum is also 0. We can assume that they might be identical. They don't have to be, but let's assume they're identical, moving at identical speeds, just opposite directions. So that was page 1. Question 4. A 0.145 kilogram baseball traveling at 35 meters per second horizontally towards a bat is struck directly back towards the pitcher at 55 meters per second. The ball is in contact with the bat for 1.8 milliseconds. Find the change in momentum of the baseball. So change in momentum, that is going to be final minus initial. I'm going to factor out the mass. And that gives me 0.145, 55 minus 35. Remember, these are going in different directions. So first we're told that it's 35 meters per second horizontally toward the bat, and then we're told it's 55 meters towards the pitcher. So these are opposite directions here. I'm going to choose that towards pitcher is positive direction. I'm just going to choose that. And then my change in momentum is 13.05 kilogram meters per second. And the only reason I chose this to be the case is because the larger speed was going back towards the pitcher. So that was why I made that choice. No real reason. Could have gone the other way. For B, find the impulse of the ball from the bat. We know that impulse is equal to the change in momentum. So the impulse is just the same as the change in momentum, kilogram meters per second. There we go. Find the average force exerted on the ball during the collision. Well, we also know that impulse is equal to force multiplied by time. So we'll have 13.05, was it? Yep. And we are looking for force. The time was 1.8 milliseconds. So that means 13.05 over 1.8 times 10 to the negative 3 to convert milliseconds to seconds. And that gives me a final force of 7,250 newtons as the average force. And now this is the change in momentum of the bat. Earlier, we found the change in momentum of the baseball. So we know that conservation of momentum is a law. So from conservation of momentum, we know that the change in momentum of the ball equals the change in momentum of the bat. They are just going to be in opposite directions. So therefore, change in momentum here of the bat is equal to the same magnitude that we had earlier, but in the opposite direction. So that was number 4. Number 5. A 1 kilogram cart moving to the right at 3 meters per second collides and sticks to a 2 kilogram cart initially at rest on a frictionless track. The collision lasts for 0.2 seconds. Find the final velocity of the carts when they are combined. So, conservation of momentum here. I got momentum of cart A plus momentum of cart B. A will be the 1 kilogram, B will be the 2 kilogram, and so I have initial momentums from both and the final momentum of both of them together. We're told that they stick together. Initially, B is at rest, so 0 momentum there. So I got the mass of A times the velocity of A is equal to the mass of A plus the mass of B, because now they are stuck together, times the velocity of both of them together. So plugging in values, I get 1 times 3 equals 1 plus 2, and velocity of AB is equal to 1 meter per second there. B, find the change in momentum for each cart separately. So we'll have cart A over here, cart B over here. Change in momentum. And just like earlier in the assignment, I'm going to factor out mass. I get VF minus VI. And the same equation over here. VF minus VI. Plugging in values. A is 1 kilogram, 1 minus 3. B is 2 kilograms, 1 minus 0. Here I get negative 2 kilogram meters per second. Here I get positive 2 kilogram meters per second. That is my change in momentum of both carts. C, find the impulse for each cart separately. Again, impulse is equal to just the change in momentum. So for A and for B, for A, we have an impulse of negative 2 kilogram meters per second. And for B, positive 2 kilogram meters per second. D, find the average force exerted on each cart separately. Separated by A and B again. Rearranging my impulse equation, I get force equals impulse over time. So I get negative 2 over 0.2 on this side. On this side I get 2 over 0.2. So here I get a force of 10 newtons. And here I get a force of negative 10 newtons. So that was question 5. Question 6. This was the one that I took off the assignment because I made a quite small oversight during the example in class, but here is the solution anyway. First, I'm going to take a look at the energy, actually, instead of the momentum. So first, EKI of the cue ball plus EKI of the 8 ball. Oh, I didn't even read it. A cue ball and an 8 ball have equal masses of 0.17 kilograms on a frictionless horizontal table. The 8 ball is initially at rest. The cue ball is struck so that just before impact, its velocity is 3.8 meters per second east. The collision is perfectly elastic. So from this, I know that energy is conserved, which is why I'm starting with energy. After the collision, the cue ball deflects east 30 degrees north. The 8-ball heads towards the pocket south of east. To sink, the 8-ball must leave the collision with a velocity of at least 1.8 meters per second east 30 degrees south. So will the 8-ball be sunk in the pocket? So as I said earlier, I'm going to start with energy because this is a perfectly elastic collision. I know that kinetic energy is conserved. So just writing out my conservation equation here. We're told that the 8-ball is initially at rest, so we have no initial kinetic energy for that. Subbing in. Oh, that shouldn't be equal. Plus, that should be equals. Canceling out, they all have the same mass and they all have a factor of 1/2. So I'm left with VIC squared equals VFC squared plus VF8 squared. From this, we should note that therefore VFC and VF8 are perpendicular to each other. Therefore, VF8 has a direction of either east 60 degrees south or north 30 degrees west. It cannot be this one. It must be this one because we are told that the 8-ball heads south of east, or in other words, east 60 degrees south. So that part was certainly important. Now, let's look at conservation of momentum. So here we are going to have momentum of the cue ball, PIC plus PI8 is equal to PCF plus P8F. Again, 8-ball is stationary in the beginning, so it has no momentum there. I'm going to have MVIC equal to MVFC plus MVF8. They all have the same mass, so I'll get rid of that as well. I get VIC equals VFC plus VF8. So this is the total momentum. I'm going to go ahead and break that up into X components and into Y components. X components. Originally, the cue ball has velocity only in the X direction. So I have VIC on the left. That is the total velocity. No need to consider an angle. It's perfectly in the X direction. The final velocity of it will be the cosine of 30 and that is the angle I'm told because it is east 30 degrees north. So if I were to draw some velocity triangles here, I would get that. Please, if you're not seeing this right away, ask me in class. I will be more than happy to show you with a diagram. So VFC cosine of 30 plus VF8 times the cosine of theta. I'm going to go ahead and erase this y. I'm going to do the y components way over here, just so I have room. Now, this theta is going to be coming from the angle that we found earlier. So this theta is going to be the 60 degrees east, 60 degrees south that we found earlier. Actually, I think I skipped over it a little bit, but the reason I got east 60 degrees south is because that is 90 degrees from east 30 degrees. from east 30 degrees north. So if I have this angle here, so east, north, south, west, if this is 30 degrees, then this angle here with 60 degrees is perpendicular. That's 90-degree angle. And over here is also a 90-degree angle, so 90 degrees there. So it could have been north 30 degrees west or east 60 degrees south, but we're told it goes south of east, so I have to choose east 60 degrees south. So that's where those two angles came from earlier. And continuing on with this calculation here, I'm told that the initial velocity is 3.8. That is equal to VC, or VFC, times the square root of 3 over 2. That is what the cosine of 30 is equal to, plus VF8 times 1/2. That's what the cosine of 60 degrees is equal to. And I'm going to go ahead and leave this equation as is for now. And I'm going to go ahead and deal with the y components. So in the y components, initially, nothing is moving with a y component. So I have 0 equals VFC. And now because I'm using y components, this is going to be the sine of 30 minus VF8 sine of theta. Again, this is 60 degrees, what we found earlier, going to both. And this gives us VFC times 1/2 from sine 30 minus VF8 times root 3 over 2. And rearranging here, VFC is going to be equal, so if I multiply everything by 2, and then I add VF8 times the square root of 3 over 2 to both sides, I get square root of 3 VF8. I'm going to take this and sub in for VFC. And that gives me 3.8 equals, so now I'm subbing in for VFC, so I get square root of 3 VF8 times the square root of 3 over 2 plus VF8 times 1/2. So from here, I'm going to go ahead and factor out VF8. So I get VF8 times, now I have square root of 3 times square root of 3. That will just give me 3 over 2 plus 1/2 is what I'm left with here. That just gives me 3.8 equals 2 times VF8. So VF8 equals 1.9 meters per second. So my final velocity for the 8 ball is 1.9 meters per second. East, 60 degrees south. So it will miss the pocket. So we are told that it needs a velocity of 1.8 meters per second. So we are going fast enough. We have 1.9 meters per second. Excuse me, but the angle is off. We needed east 30 degrees south. Instead, we got east 60 degrees south. So that was the solution for number 6. A little bit trickier. Question 7. This is a center of mass question. So Jupiter is the most massive planet in the solar system, and it orbits the sun in a nearly circular path. Both the sun and Jupiter orbit their common center of mass, otherwise known as a barycenter. Part A, calculate the distance of the center of mass of the system to the center of the sun. So here's the sun. That's the center of the sun. Over here's Jupiter. Obviously, this is not drawn to scale. And we want to know where the center of mass is along this line here. Our calculation for that is xcm, so the center of mass, times the sum of all the masses multiplied by their radii. So that's the mass of the sun times the radius of the sun added to the mass of Jupiter times the radius of Jupiter. And actually, I'm misspeaking there. It's not the radius of the sun and the radius of Jupiter. It is the distance of the sun to a reference point and the distance of Jupiter to a reference point. On the bottom, I have the mass of the sun plus the mass of Jupiter. And we will plug in some numbers shortly. I am told, if you look at the formula sheet over here, I'm told that I have the distance of the sun to Jupiter. So I know the distance from sun to Jupiter was 778 times 10 to the 6. So I'm going to call that 778 times 10 to the 9 meters, because that other number was in kilometers. So I know this distance here. I'm just going to label this Jupiter and Sun. There we go. I also know the masses of both objects. Here I used 1.99 times 10 to the 30. And here I got 1.9 times 10 to the 27. Both of these are in kilograms given to us. And so this is what we are told. I don't believe I gave you anything else on the formula sheet. I also told you the radius of the sun was 6.96 times 10 to the 8 meters. So writing that off to the side, our sun equals 6.96 times 10 to the 8 meters. Just going to double check that I actually wrote that right. 6.96 times 10 to the 8 meters. Nice. Okay. So I need to figure out where along this line the center of mass is. It is located somewhere. I need a reference point to measure this between. So I'm going to say that my reference point is here. This is 0 meters, which makes this point over here equal to the distance 778 times 10 to the 9 meters. So because I'm going to use the center of the sun as my reference point, that means the distance from the sun to the reference point is 0. So this chunk of my equation is equal to 0. Another little hint towards what reference point you should use was in the question itself, actually. So I'm going to reread part A here. Calculate the distance of the center of mass of the system to the center of the sun. So I ask you to find the location of the center of mass in reference to the center of the sun. That should give you a hint towards where the center of mass of the system should be, and that, or the reference point should be, and that is the center of the sun being your reference point. So with that, I'm going to have the mass of Jupiter times the distance of Jupiter to our reference point, in this case that is the center of the sun, over the sum of both the masses. So that is going to give me 1.9 times 10 to the 27 multiplied by 778 times 10 to the 9, all over 1.9 times 10 to the 27. And I just realized I'm writing the masses backwards here. That's okay. And I get a final answer of 7.42 times 10 to the 8 meters. So that is my distance there. Compare your answer to the radius of the sun, which I have written off to the side still, which is larger. So comparing the two, I see that XCM is larger than the radius of the sun. So going back to my little diagram here, that would put XCM right about there. That's going to be my 7.42 times 10 to the 8 meters. And this distance here is the radius of the sun. That is our 6.96 times 10 to the 8 meters. So the center of mass of this system is actually outside of the sun. It's not inside of either object. It's outside of the sun. So that was question 7. And I believe this is the last one, question 8. Yes, and then there's a bonus. So, question 8. A projectile of mass 0.05 kilograms is launched horizontally at a speed of 200 meters per second into a mass of 2 kilograms hanging on a pendulum. Assume the pendulum pivots without friction and that the mass of the rod of the pendulum is negligible. This part is actually important, that it is a rod and not a string. Get back to that later. The projectile embeds itself into the hanging mass, and the now combined masses swing upwards together. Part A, what is the maximum vertical displacement of the hanging mass and projectile? So there's essentially 2 parts here. First, conservation of momentum to find the common speed of the two, and then conservation of energy. So here we have the momentum of the projectile initially, and the mass is hanging and at rest initially. And here I have the mass of the projectile plus the block, or the hanging mass, whatever you want to call it. I guess I'm imagining it as a block. Doesn't really matter. Plugging in values, again, 0.05 times 200 equals 0.05 plus 2 VF equals 4.88 meters per second. And then conservation of energy, I have the initial kinetic energy of, so the final velocity of both the projectile and the mass together after the collision is 4.88. This is also the initial velocity for both masses together. So in my conservation of energy here, I'm going to have 1/2 mvi squared equals mgh. At its highest point, the maximum vertical displacement, it'll be motionless for that moment. At the beginning, we're just going to assume that before it starts swinging upwards, before it starts moving, we're going to call that our vertical reference point. So we have 0 gravitational potential energy at that point. And we are going to solve this for h. So h equals vi squared over 2g. The masses cancel in this case because this mass is on both sides, is both of the masses added together. So the m in this case for energy, for the conservation of energy equation, is 2.05 kilograms on both sides. Cancel that out. Plugging in, h equals 4.88 squared over 2 times 9.8, and that gives me about 1.22 meters for part A there. B, if the pendulum has a length of 1.5 meters, find the angle between the pendulum's initial position and its position at its maximum height. So initially, pendulum is here, and this is a full 1.5 meters long, and eventually it will swing out to a side. If this is its maximum height here, we know that this height we just calculated is 1.22 meters. It's asking us to find the angle between here. So it wants us to find this angle, the angle between the pendulum's initial position and its position at its maximum height. So if I were to turn this into a triangle, a right angle triangle, that means that this height here is 0.28 meters. We know that this length is also still 1.5 meters. So redrawing this little triangle, we have 0.28, 1.5. That is enough for us to find the angle here. So the cosine of the angle theta is equal to the adjacent 0.28 over the hypotenuse 1.5. So theta equals the inverse cosine of 0.28 over 1.5. And theta equals about 79 degrees. And that was the full assignment. The reason why I said the rod of the pendulum is for the bonus question. It does matter. If instead this was a string, you would have to make a couple of different other assumptions, and it actually does become more complicated because then you have to account for the tension in the rope. But because this is a rod, it's a rigid rod, we don't have to account for that when it comes to this bonus question here. So refer to the pendulum in question 8. What is the minimum speed of the projectile before the collision needed to make the pendulum swing around a full 360 degrees? So essentially we're just working backwards here. And I'll show you where the little trick is when I get to it. So we know that the kinetic energy of the projectile and the mass, the pendulum, together has to be equal to the final gravitational potential energy. So just like how we had before, MVF squared, MVI, MGH, and again, masses cancel. In this case, this is where the mass is still 2.05 kilograms here. Rearranging for VI, I keep writing F for some reason. I get the square root of 2GH. Now plugging in, this is where things start to matter about how we set it up. Height here I'm saying is 3 meters. Looking back, that is because our pendulum is 1.5 meters long. So, if the pendulum pivots around this point, has a mass here. If this here is 1.5 meters, and this here is 1.5 meters. That's messy. Tried to save it, but I gave up. So we need this pendulum to swing all the way around to the top. And we just needed to have a minimum velocity to get it to the top here. So if we solve for the exact velocity it needs to get to the top, we know that that is the velocity that would theoretically get it stuck at the top. So just any amount over that. So we will solve for the perfect scenario, and our answer will just be noted that anything greater than that value will provide us with the amount of kinetic energy we need in the beginning. So, and this is also why I'm using a full height of 3 meters, because When the mass is all the way up at the top, that is a 3 meter difference. So that is why our height is 3 meters here. And so we have an initial combined velocity of 7.67 meters per second. This is for the mass and the projectile. So, punching this in to now conservation of momentum, we get that the initial momentum has to equal the final momentum. And initially, the projectile is the only thing that has momentum. At the end, we know that we have little mass plus big mass, and the final velocity. And remember, this is the final velocity we just found earlier. Because this is the final velocity of both masses together, and that is what we just found. So, plugging in and solving for the initial velocity of just the projectile together. I get 314.47 meters per second. So, actually, I won't do that. So, therefore, the initial velocity of the projectile must be greater than 314.47 meters per second. And again, that is because this exact speed of 314.47 meters per second, that is only enough speed to get the mass to stop at the very top. That is only enough to get it at the maximum height possible for this pendulum. And you need just a tiny bit more to have it continue going. So if you add just a bit more speed, it will have slightly more kinetic energy than it could ever have gravitational potential energy. So then you know it would continue around in a circle. If it hit it at exactly 314.47 meters per second, the pendulum would just be stuck upside down or right there at the top. So lastly, this also again only works for it being a rigid rod. If it was a string instead of a rigid rod, it must go faster for the string, because otherwise the string would go slack before it even gets to the proper heights there. So it would actually have to end up going faster for a string. So that was assignment 10. Thank you for watching. Email me if you have questions or ask in class.